Hi everyone, welcome back to MATA35. Today we're going to be talking about matrix ODE representations. So basically, last time we talked about systems of first-order differential equations. It turns out that you can rewrite those as matrices, and then you can use some of the techniques we learned from linear algebra to work on finding solutions to these matrix ODE systems. And so that'll be the topic of today, the first half of lecture. So let's go ahead and get started. Let's see. So, last time we had these homogeneous first-order ODEs, things like this. It turns out we can rewrite them as a matrix ODE. So if you look at this example here, you can think of this here as, say, something like z dot is equal to AZ, where A is this 2 by 2 matrix, and Z is equal to XY. And so, for example, we have something like, let's say, X dot Y dot is equal to 1, 0, minus 4, 2 times XY. And when you, of course, since this is matrix multiplication, when you rewrite this out, this is basically just saying X dot Y dot is equal to, well, what is this vector? This is 1 times x plus 0 times y. That's x. And the bottom is minus 4 times x plus 2 times y. Okay, so we've taken a system of equations and we converted them into a single matrix. So this is sort of like the matrices that we converted systems of linear equations into, except now the system of equations defines an ordinary differential equation. So basically, we can rewrite homogeneous first-order ODEs as just a matrix vector ODE. And the matrix form equation, z dot is equal to AZ, has solutions. Has solutions, and when we say z of t, we mean a vector, a two-dimensional vector, x of t, y of t. So, for example, suppose that z, one solution to the example we had earlier, would be e to the t for e to the t minus e to the 2t. What does that mean? Well, that means that when we take z dot is equal to az and we plug these things in, so what do we get? So we're trying to plug in e to the t for e to the t minus 2e to the 2t. Oh, wait, sorry. I just did something wrong there. So when we plug this in, what we want is we want this derivative to be equal to, to some equation. So let's try writing this out. So hopefully I got the right answer here, but we'll see if I did or not. So minus 4 and 2, and we want to multiply this by xy, so that's e to the t. Oh, sorry, that was my mistake. There needs to be a, say, minus 2e to the 2t. So e to the t, minus 4e to the t minus 2e to the 2t. And when we multiply this out, what we get is e to the t minus 4e to the t, since that's minus 4 times the top component of the vector, plus 8e to the t minus 4e to the 2t, which is equal to e to the t 4e to the t minus 4e to the 2t. And if you check, that is z dot. Okay, so even though z here is a vector, we still can describe it as a solution to this matrix form equation, z dot is equal to az. Okay, so now we've done that, there is the question of, well, what's a solution? How did you get the matrix with just the digits? Can you re-explain that? Okay, yeah, so let's take a little bit longer and explain what we're doing up here. So, I gave an example over here, but let's give an example with just with all the variables. So, if we have z dot is equal to az, what is this matrix equal to? So when you multiply this out, that's equal to az plus by ax plus by cx plus dy, right? Because that's matrix multiplication. When you take a 2 by 2 matrix and multiply it by a 2 by 1 vector, you take the inner product of the first row and the vector, and then the inner product of the second row and the vector. Okay? So basically, this entire equation is just saying x dot y dot is equal to ax plus by cx plus dy. Okay? And so you'll notice that if you just take a look at the top component, these two are entirely equivalent. Does that make sense? So you have to remember back to the linear algebra we spent a couple weeks on. All we're doing is we're encoding this system of equations as a matrix times a vector. And so that's what we did with the matrix up here as well. So that's what we did up here, is we took that and we just did matrix multiplication, and you get this piece here. Does that make a little bit more sense to people? If this is confusing, we should take some time on it because I'm a little lost. Ah, yes, what does this help us solve? Well, right now, not yet anything. But what we're going to do is show you a method to use this matrix and then use the eigenvalues and eigenvectors of the matrix to let you solve the original equation. So this is a system of equations. So this is a system of equations, right? Or let's say if we originally had a system of equations, x dot is equal to x and y dot is equal to minus 4x plus 2y. Okay? So if originally we have a system of equations, in the very last lecture, we described how to solve some of these things, right? So what you can do is you can take the an extra derivative of x dot, get x double dot is equal to x dot, and then you plug in y, and we had an entire procedure for solving a system of two ODEs, right? So now what I'm going to be giving you in today's lecture is a different way of solving the system. That makes use of linear algebra instead. And sometimes this will be easier. Sometimes it'll be harder. Sometimes it'll be easier. It just depends on the problem. Okay, let me move on. Sorry, did that make a little bit more sense? So basically, we're converting this equation into a different form. That's a matrix. And then somehow this will help us solve the system. Okay, this will hopefully be a little bit more clear when I show you a couple examples. Can you explain the second thing you did, the matrix part? Oh, sorry, down here. Yep. So are you talking about this area? So down here, what we did is, I'm just saying that you also have solutions. So we didn't actually, I haven't solved it yet. I just gave you a solution out of thin air. So in the, basically I'm just saying that there is some equation for z. So you can think of z as equal to xy, right? So basically what you're saying is that if x is equal to e to the t and y is equal to 4 e to the t minus 2 e to the 2t, that is a solution to the original equation. And what we did is we double checked that it was a solution. So we plugged that in and we checked that yes, it is indeed a solution. Now, how do you get that solution? Well, we haven't taught you that yet. That's what we're doing in today's lecture. So basically, there is a quick way of getting that solution, which I haven't explained yet. Okay, so let's go on and actually talk a little bit about how we solve these matrix form equations. So, well, this maybe I got this in the wrong order, so I apologize about that. So basically, there is a way of solving matrix form equations. And to explain this method, let me talk a little bit about, go back to single variable ODEs. So let's suppose that y prime is equal to ky. Well then, we solved over the last couple weeks that y is equal to some constant times e to the kx for single variable ODEs, right? So this is something you can pretty easily figure out from either using the method for constant coefficient linear first order systems, or you can use an integrating factor, and this also allows you to solve it. Or actually often you can just use separation of variables, and that will also allow you to solve this. Okay, so that was something we solved earlier. So this is for single variables. So now, one guess you might have is that for this multivariable, this matrix system, maybe there is a solution z is equal to e to the lambda t, times v. So we're going to use t instead of x here because that's what we're using for the independent variable when we have multiple variables. So maybe there exists some solution that looks like this. So this is our guess, and this is something we're guessing because we know that the well, for single variable ODEs, we have this e to the kx. So let's call it e to the lambda t here. And we're going to guess that instead of just a constant, we're going to have some vector. Okay, so that's not quite true, but basically the idea is we're guessing that this is some form of a solution for some constant lambda and for some vector v. So now, if this is a solution, then it has to satisfy the original equation, right? So if you take this and you plug it in, then that should satisfy your original equation if this is a solution. And so let's try doing that. So what is z dot? Z dot is then going to be equal to lambda e to the lambda t times v. And we know that z dot is equal to az. So lambda e to the lambda t times v is equal to a times z, which is e to the lambda t times v. And so if we rearrange this a little bit, we have e to the lambda t times lambda v is equal to e to the lambda t times av, which means that lambda v is equal to av. Now this should be this should remind you of something, right? That was exactly the equation for eigenvector and eigenvalue problems, where it's some vector that if you multiply it by a is just lambda times that vector. So this is exactly the eigenvector eigenvalue question. So that means that if z equal to e to the lambda t times v is a solution, then lambda v is an eigenpair. So does a equal to lambda? No, so this is something that you should remember from our eigenvector discussion. So remember, if you had, say, 1, 1, 1, 1 as a matrix, and you multiply it by, let's say, 1, 1, then that is equal to 2, 2. And so this here is a, this here is something like z, and this here is 2 times z. And so you had an eigenvalue 2 for this eigenvector 1, 1. Remember, in order to find the eigenvalues and eigenvectors, what you did is you took lambda minus 1 minus 1 minus 1 lambda minus 1, and then you set that equal to 0. And that allows you to compute the eigenvalues. Okay, so you have to remember that we had this entire linear algebra section where we computed eigenvalues and eigenvectors, and now we're using those. So we're using those ideas and coming back and using them to solve these matrix form ordinary differential equations. Oh, because so the equation for eigenvalues is lambda v is equal to av. So that means that 0 is equal to av minus lambda v. Or you can think of it as lambda v minus av is equal to 0. So lambda times the identity minus a is equal to 0. You could also do 1 minus lambda, 1, 1, 1 minus lambda. So this is just the equation for computing eigenvalues and eigenvectors, which we had back in lecture 5, I want to say, 5 or 6. I don't remember anymore. Okay, so note that this is exactly the eigenvalue eigenvector question. And so, therefore, for each eigenpair, and this is true for any eigenvalue eigenvector pair, for each eigenpair, e to the lambda t times v is a linearly independent solution. So remember that if we have many different linearly independent eigenpairs, then we can get that. So that means that if we have many different linearly independent eigenpairs, you can get many different linearly independent solutions. When you multiplied A and Z matrices, is the solution 2Z or AZ? I'm a little bit confused by the question. So basically, what we said is that AZ, for this particular matrix, AZ is equal to 2Z, and so therefore you had an eigenvalue lambda equals 2, and eigenvector V is equal to 1, 1. Yeah. Okay, so this is all just a really long-winded way of saying that it turns out that eigenvalues and eigenvectors, which we used earlier for Leslie matrices, remember? So we used the eigenvalues and eigenvectors to be able to compute multiplying by a Leslie matrix many, many times. It turns out they have this other use, which is if you can compute the eigenvalues and eigenvectors of the matrix associated to a matrix ordinary differential equation, that allows you to get the solution to the ordinary differential equation. So let's state this again. So if we have z dot is equal to az, where A is an n by n matrix and z of t is a length n vector, then if lambda 1 v1, lambda 2 v2, all the way through lambda n vn is an eigenbasis. So remember, an eigenbasis means that any vector in your space can be written as some combination, linear combination of your eigenvectors. Well, then a solution, the general solution to z is equal to c1 v1 e to the lambda 1t plus dot 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 plus, well, I should have another plus there, plus cn vn e to the lambda nt. That's the general solution. So once you have the eigen decomposition, once you have an eigenbasis for a matrix, you immediately know the answer. Let's see this. So let me do it in a 2 by 2 case. I will only so for most examples we're only going to do the 2 by 2 case. So let's go back to the matrix we had earlier. So A is equal to 1, 0, minus 4, 2. Okay? And I chose this matrix because its eigenvalues are really easy to compute. Its eigenvalues are just 1 and 2, because those are the diagonal entries of the matrix. And this is a triangular matrix. So remember, we spent a lot of time computing these eigenvalues and eigenvectors, and for a triangular matrix, the eigenvalues are just along the diagonal. And the next thing we need to do is we need to compute the the eigenvalues are on the diagonal, and we need to compute the eigenvectors. So lambda 1 is equal to 1. Well, that means that 1, 0, minus 4, 2 times some vector xy is going to be equal to xy. Because what we're saying is that a times v is equal to, or a times z is equal to 1 times z. And so that's the equation we need to solve. And when we solve that, what you get is that, well, x is equal to x, and minus 4x plus 2y is equal to y. And x is equal to x doesn't mean anything. X is always equal to x. And so you end up being left with just y is equal to 4x. Okay? So y is equal to 4x, which means you have an eigenvector. Well, if y is equal to 4x, you can set x equal to 1, and y is then equal to 4. So therefore, you have an eigenvector. v1 is equal to 1, 4. Oh, what happened to the y? Let me go through all the steps of this. So if we take this here, if we subtract 2y from both sides, you're left with minus 4x is equal to minus y. And so therefore, y is equal to 4x. Because we subtracted 2y from both sides, and then we multiplied by negative 1. Okay, so that was one of our eigenvectors, and then we need to compute our other eigenvector. Lambda 2 is equal to 2. And so that's, we have the same matrix, but instead we have some vector, xy, where if you multiply it, you get 2x, 2y, because that's our eigenvalue, right? And so we need to solve this as well. And so you get x is equal to 2x, and minus 4x plus 2y is equal to 2y. Well, when you solve these, you end up getting that x is equal to 0, and, well, y is equal to y, which doesn't mean anything. So v2 is then equal to, well, x is equal to 0, and y can be anything. So it's 0, 1. Okay, so this is our full eigendecomposition for this matrix. And that means that once we have the eigendecomposition, we immediately know that, so this was the z dot is equal to az. And so then you immediately know that z is equal to some constant times 1, 4 e to the t plus some other constant times 0, 1 e to the 2t. Or you can also rewrite this as c1 e to the t and 4 times c1 e to the t plus c2 e to the 2t. So this is the general solution. Oh, sorry. And you'll notice that one example, if we set, say, C1 is equal to 1 and C2 is equal to minus 1, then we're left, let's say minus 2. Remember, I gave you this example, 4e to the t minus 2e to the 2t. It turns out that this is a specific example for some initial values. And so if you set that, then you are left with e to the t, 4e to the t minus 2e to the 2t. Okay? Does anyone have any questions? This is a lot to take in, because we're connecting together all the linear algebra stuff we did now to... Oh, why did I set C to that? No particular reason. You can set C to anything you want. I just wanted to give show you that if you set C equal to that, then you get the equation then you get this guess that we had back here. So basically, I told you that this was a solution, and I'm just showing you that it is indeed a solution when we solve it this other way. So remember, of course, when you have just these general constants, you can set them to whatever you want. And I just set this as a particular example of something you could set the constants to. So normally, the reason you would set the constants would be if I gave you some initial values. I didn't give you any initial values this time, but you can still, which means that you have this general solution, but you can choose any initial values you get to get specific solutions. Okay, so just to repeat everything, how did you get the final matrix? Oh, well, I plugged C1 and C2 into that matrix. So I chose arbitrary C1 and C2, and I plugged them in. Okay, but the basic point of this is, remember, when we had a higher order linear the C, Z, yes. So this is just the formula. If this is what you're asking, this is given as a formula. You should memorize it, because this formula is basically the same as the formula that we had for higher order linear differential equations with constant coefficients, right? So you had C1 e to the lambda t plus C2 e to the lambda 2t, etc. And so it turns out that when this is a matrix, well, you then have to add on these eigenvectors in addition. But basically, it's the same idea as the higher order linear differential equations with constant coefficients. Any other questions? The basic idea is, of course, like previously we had the characteristic polynomial, and once you solved for the roots of the characteristic polynomial, you immediately knew the general solution, right? Here, it turns out that we have this characteristic matrix, and when you solve for the eigenvalues of this matrix, then you end up immediately with the general solution to your problem. And this is actually the reason why we called the roots of the characteristic polynomial eigenvalues, is because they play the same role as the eigenvalues in these matrices. And in fact, it turns out that they are the same as these eigenvalues under some interpretation of the problem. Okay, that was your confusion. Yes, so let me take a little bit longer. So I'm going to give myself a little bit more space up here. Let me turn off my stats for a moment. So we had C1 14 e to the t plus C2 01 e to the 2t, right? So then, when you multiply it in, what you get is this vector here is C1 e to the t and 4C1 e to the t. Plus this vector here, well, the top is 0, so that multiplied by anything is still just 0. And C2 e to the 2t. So then you just have these two vectors that you're adding together, which is then equal to C1 e to the t, and the bottom entry is 4C1 e to the t plus C2 e to the 2t. Yep. Okay, so again, I've repeated myself a couple times, but that's important. So another question. Sorry, can you write the step how x is equal to 0 and y is equal to y? Yeah, sure. So the step for x is equal to 0, this here, is subtract x from both sides. So if you subtract x from both sides, you're left with x is equal to 0. Or 0 is equal to x. And then once 0 is equal to x, you plug that in to, so this thing here is just 0. So 2y is equal to 2y. Divide both sides by 2, you get y is equal to y. Why did you subtract x? Because you want to try to figure out what x is equal to. If I tell you that some number is equal to twice that number, what is that number equal to? The only number that's equal to twice itself is 0. Okay, so now let's go back to the application that we started working on last time, at the end of class last time, but ran out of time for. So, and we're going to solve it two different ways. So again, we have some amount of galactosyl-human serum albumin. So this is some compound that's injected into a patient's bloodstream to measure liver function. We have the blood, that's up top, and we have the liver, which is down bottom. Let's say that the TCGSA is transferred from the liver to the blood. Transferred from the blood to the liver at 6% per minute. So if this is transferred at 6% per minute, and from the liver, from the blood to the liver at 6%, and from the liver to the blood at 3%, we want to know how much TCGSA is in the blood or liver as a function of time. So one thing you can do is you can assign different variables. So let's say this is L of t. L of t is the amount of, let me use a different color that shows up a little bit better. So this is the amount of TCGSA in the liver, and we have the amount of TCGSA that's in the blood. And initially, so we know our initial conditions. So initially, the amount in the blood, B of 0, is equal to 3 milligrams, because we injected that in. And we know that initially, the amount in the liver, we're going to say is 0 milligrams. Okay, so those are our initial conditions, and we can write this out as a two-compartment model. So we have B, and we have L. And how much goes from the blood to the liver? Well, 6%, right? So that's 0.06 B. How much goes from the liver to the blood? Well, that's 3%, so 0.03 L. And you can write this as a system of differential equations. B dot is equal to minus 0.06 B plus 0.03 L. And L dot is equal to 0.06 B minus 0.03 L. And so now I'm going to solve this two different ways. First, I'm going to solve it using the method we used last Friday. So we're going to take extra derivatives, we're going to substitute to get rid of one of the variables, and we're going to solve it as a single variable ODE. And then the next thing we're going to do is we're going to show that you can solve this using the matrix form by looking at eigenvalues and eigenvectors as well. And you will get the same answer. So we have this equation. What do we do? So the first thing that we did last time is we took the second derivative of b. So b double dot is equal to minus 0.06 b dot plus 0.03 L dot, because you're taking the derivative again with respect to t. So then b double dot is equal to, and we know what L dot is, so it's minus 0.06 b dot plus 0.03 times 0.06 b minus 0.03 L. So note that in this first step, what we were doing is get second derivative, and then get rid of L dot. So let's rewrite that. So that's b double dot is equal to minus 0.06 b dot plus 0.0018 b minus 0.0009 L. We know what b dot is too. Why don't we use it? So the trick here is that we could use it. So we could also plug in b dot. But the problem is if we plugged in b dot, we'd get L back. So we're trying to get rid of one of our variables. You can either, what you want is you want to have a single variable ODE, because we know how to solve single variable ODEs. And so we don't need to get rid of b dot because we're getting rid of all the L's right now. Because remember, what we're trying to do is we're just trying to simplify the equation to turn it from a two-variable equation into a one-variable equation. And so you don't want to end up with having both of the variables in there. And so in fact, we are going to use the first equation, but we're going to use it in a different way. Instead of getting rid of b dot, we're going to get rid of L using the equation. So you'll notice that if you rewrite this, this is precisely 0.03 L is equal to b dot plus 0.06 b. And so let's multiply by 100. 3L is equal to 100 b dot plus 6b. And L is equal to 100 divided by 3 b dot plus 2b. Okay? So we're going to use that first equation, and instead of using it to get rid of b dot, we're going to use it to get rid of L. So we're going to use this fact here, and we're going to plug that in for L. So that's going to be this step here. So then b double dot is going to be equal to minus 0.06 b dot plus 0.0018 b minus 0.0009 times 100 divided by 3 b dot plus 2b. And if we simplify it a little bit more, we get b double dot is equal to minus 0.06 b dot plus 0.0018 b minus 0.03 b dot, because we multiplied by 100 and divided by 3, minus 0.0018 b. Notice that these two happen to cancel out. They won't always, but this time they do. And so what we're left with is b double dot plus. Let me do this. Let me do all the steps. I was about to skip a step, but let's not skip any steps. B double dot is going to be equal to minus 0.09 b dot, and therefore b double dot plus 0.09 b dot is equal to 0. Okay, so notice we started with a system of two first-order differential equations with two variables. What we're left with is now a second-order differential equation with just one variable. Once we do that, so notice that we have a couple different things. So we're going to first start with this sign, and I'm just going to copy this down because we're going to need that later when we solve back for L. So first, well, we know how to solve a higher order linear differential equation with constant coefficients. You just look at the characteristic polynomial. The characteristic polynomial here is lambda squared plus 0.09, not b, lambda, 0.09 lambda is equal to 0. And therefore, lambda times lambda plus 0.09 is equal to 0. So lambda is equal to 0 or minus 0.09. And what do we do? How do we find the general solution to this equation? Well, b is then just equal to some constant. So this is the general solution times e to the 0 times t plus some other constant, e to the minus 0.09 times t. And therefore, b is equal to c1 plus c2 e to the minus 0.09 t. Because, of course, e to the 0 is equal to 1. So this is one of our solutions. And the next thing we need to do is we just need to plug in, because we have an equation for L in terms of b dot and b. So then we can also solve for L. So when we do that, well, note that b dot is equal to minus 0.09 c2 e to the minus 0.09 t. Let's just take the derivative of the blue underlined equation. And therefore, we have L is going to be equal to 100 divided by 3 times b dot. Well, 100 times 0.09 is 9. Divided by 3, that's 3. So we get minus 3 c2 e to the minus 0.09 t. plus 2 times b, so that's 2 times c1 plus 2 times c2 e to the minus 0.09t. And then we get L is equal to 2 times c1 minus c2 times e to the minus 0.09t. And this solves this equation. Okay, so that gives us the general solution to B and L. And of course, we also, any questions so far? So basically, we converted it into a single variable ODE, and then we use the characteristic polynomial to solve for one of the variables, and we plug that in to solve for the other variable. Yes, exactly. So now we should use the initial values. So now we have these two equations. B of t is equal to some constants times e to the minus 0.09t, and L of t, we also have a formula for that. And we had our initial values, which were 3 milligrams and 0 milligrams. And you can plug this in. You get 3 is equal to b of 0 is equal to c1 plus c2 times e to the minus 0.09 times 0, which is equal to c1 plus c2. And you also get 0 is equal to L of 0 is equal to 2c1 minus c2 times e to the minus 0.09 times 0, which is equal to 2c1 minus c2. So I'm going to add these two equations together. You'll get 3 is equal to 3c1. So c1 is equal to 1. And when you plug that back in, you get c2 is equal to 2. And that allows us to know exactly what our original, plug those back in. So b of t is equal to 1 plus 2 e to the minus 0.09 t. And L of t is equal to 2 minus 2 times e to the minus 0.09 t. And what was our original question? How much blood TCGSA is in the blood or liver as a function of time? This allows us to completely solve that. And in fact, one other interesting question is how much is there when at time infinity? So this is our answer. I'm just going, and in fact, we can plot these out. And if you plot these out, you end up getting something that looks like, oh, actually, let me do one of these in 1, 2, 3. At b of 0, let me do one of these in a different color, actually. Let's do this one in green. So at b of 0, this is equal to 3, and then it goes down to exponentially and then approaches 1. And we also have that L of 0 is 0, and it goes up exponentially until it reaches around 2 asymptotically. And so you could plot this out now that we found the actual equations. Okay, any questions about that? You can also see this because the limit as t goes to infinity of b of t is equal to 1 milligram, and the limit as t goes to infinity of L of t is equal to 2 milligrams. So now you might be wondering, well, we know how to solve this because we solved this last Friday. Why do we care about doing all this complicated matrix stuff? Yes, to answer your question, you just sub in the values after doing all the first steps. But now, the question is, that took a long time, right? Because we had to do several different steps. We started here, we had to convert it into a single variable ODE, then you had to solve the single variable ODE, plug it back in to get the other equation, and then solve for the initial value problem. You can also solve this as a matrix equation, and sometimes that's faster. So, we have our original equation, and we can convert that. So our original equation is here. You can convert that into this matrix equation. Right? When you multiply out the matrix times the vector, you get back exactly the original equation. And it turns out that when you do that, you can do an eigendecomposition of that matrix. So how do we solve for the eigendecomposition? Well, you take, lambda I minus the matrix is equal to the determinant of this is equal to 0. So that's what we do. And so that gives us lambda plus 0.06 minus 0.03 minus 0.06 and lambda plus 0.03. And we know that that's equal to 0. And so this is equal to lambda squared plus 0.09 lambda plus 0.0018 minus 0.0018 is equal to 0. And when we rewrite this, you get lambda squared plus 0.09 lambda is equal to 0. Lambda times lambda plus 0.09 is equal to 0. And therefore, our two eigenvalues are 0 and minus 0.09. Notice that the equation we got here for the characteristic polynomial is exactly the same as the equation we got back here. Wait, sorry, where was I? Is exactly the same as this equation. Lambda squared plus a minus lambda I. Oh, that also works. A minus lambda I, and if the determinant of a minus lambda I is equal to 0, then the determinant of lambda I minus a is equal to 0. You can do it either way. It's just the negative sign. But yeah, so notice that the equation we get, this equation, is precisely the same as the equation we get when we solve it as a matrix to solve for the eigenvalues. And this is exactly why we call them eigenvalues. Okay, but now we have the eigenvalues, and now since we're doing this as an eigendecomposition, we have to solve for the eigenvectors. So we have lambda 1 is equal to 0, and so when we're solving for that, we get minus 0.06, 0.03, 0.06, minus 0.03, times xy is equal to 0, 0, since this is an eigenvector corresponding to the eigenvalue 0. When you solve this, you'll end up getting minus 0.06b plus 0.03L is equal to 0, and so L is equal to 2b, and V1 is equal to 1, 2. Okay, I'm doing this a little bit fast, but basically I'm just solving for eigenvectors in the same way as I did on the previous example for eigenvectors and eigenvalues. And we have lambda 2 is equal to minus 0.09, and so you do the same thing, minus 0.06, 0.03, 0.06, minus 0.03 xy is equal to, oh sorry, I shouldn't be using xy, I should be using b and l. So this is b and this is l. You can also use x. What is different? Nothing. That's exactly my point. Nothing is different. So this is minus 0.09 b minus 0.09L. And when you solve this, you get minus 0.06b plus 0.03L is equal to minus 0.09b. And so 0.03L is equal to minus 0.03b. L is equal to minus b. So then V2 is going to be equal to 1 minus 1. Okay, so that is our eigendecomposition. So we can solve for the eigenvalues and the eigenvectors. And once you've done this, so you have to do this different process for solving it. Once you've done this, you immediately know the general solution. BL is equal to C1 times e to the 0t times this vector 1, 2, plus C2 e to the minus 0.909t times this vector 1, minus 1. And so you can rewrite this out. BL is equal to C1 times 1, 2, because e to the 0 is always equal to 1, plus C2 e to the minus 0.09t times 1 minus 1, which is precisely equal to C1 plus C2 e to the minus 0.09t and 2C1 minus C2 e to the minus 0.09t. Notice that what this means is that we have B is equal to C1 plus C2 e to the minus 0.09t. And that's exactly what we had here. B is equal to C1 plus C2 e to the minus 0.09t. Similarly, we had L is equal to 2c1 minus c2 e to the 0.09t. And we had L is equal to 2c1 minus c2 e to the 0.09t. And of course, then you can plug back into the initial value problem can then be solved by plugging in. And that's going to be no different because we got to the exact same point for the general solution. So this is a way of solving multivariable ODEs, which means we don't need to do the substitution way that we learned before. So if your multivariable ODE is homogeneous, yes, this is a different way of solving the multivariable ODEs, so you don't need to do the substitution way that you learned before. Sometimes, though, the substitution, if you have an inhomogeneous ODE, then you do still need to use the substitution method. Because note that this method only works when you have the equation z dot is equal to az. So if you have any t's in there, then you can't use this method. Not easily. There is a way of extending this method to that, but we're not going to cover it in this class because it's significantly more complicated. Because remember, when you have inhomogeneous equations, then things get a little bit more complicated, and then you have to use an ansatz. You can also use an ansatz for these matrix form equations, but we're not going to. How would it look with t's in there? Oh, so if there were t's in here, you might have something like z dot is equal to az plus, say, t1, some other vector with t's in it. Because the vector A, the matrix A doesn't have any t's in it, and the Z also doesn't have any t's in it. So you might have something that looks like that for the inhomogeneous version. And if it has t's in there explicitly, then we haven't taught you how to solve them in this matrix form. And so if you see t's in there, then you will have to use the substitution method. The other way is, of course, you can solve it using this method and then guess an ansatz in the sort of matrix form. If this were B44, that would be something we would teach you. But inhomogeneous means that you have a non-constant. So that's a little bit complicated, and I actually wrote up a Piazza post about this. But inhomogeneous means that it has a t component that isn't multiplied by x or y. In the case of a constant coefficient ODEs, which is what we're working with right now, it'll be inhomogeneous if it has any dependence on t or on like 1. So for example, if I had z is equal to az plus 1, 1, that is also inhomogeneous. So if it depends on anything other than something multiplied by x and y. Okay, but let's not worry about that for now, and let's just try this out. So, this was a lot, but suppose I gave you this equation. X dot is equal to minus y dot is equal to 3x plus 2y, and x of z is equal to AZT would be homogeneous. Yes, but it would not be constant coefficients. And so it would not be constant coefficients, which means that this method also doesn't work. So this method doesn't work unless you have constant coefficients and you don't have another piece. So basically, I'm teaching you this method only works for constant coefficient homogeneous. So it needs both. Okay, so now we have this equation. So the first step is let's convert to z is equal to az, where z is equal to x, y. So let me reset the chat. What is the correct conversion here? Okay, yeah. Wait a moment. Yes. That's right. My notes are messed up. Yep. So this is precisely, well, we have a 1y, so that's, and 3x plus 2y. So this is indeed d over here. Oh, sorry, wrong way. next thing that we do, find the eigenvalues. So let me reset. And what we need to do is find the eigenvalues. Which of these are the eigenvalues of that matrix? So note that our matrix A is equal to 0, 1, 3, 2. And so if you wanted, you need to take the determinant of either A minus lambda I, which is also is equal to 0, or you need determinant of lambda I minus A is equal to 0. Yes, use determinants if it's not a triangular matrix. It turns out that if you use the determinants when it's a triangular matrix, you will still get the right answer. It will still work out. It's just that when it's triangular, you have that quicker shortcut. Okay, so yeah, so let's see what this is. This is lambda minus 1 minus 3, lambda minus 2. This is equal to lambda squared minus 2 lambda minus 3 is equal to 0. Lambda minus 3 times lambda plus 1 is equal to 0, so lambda is equal to minus 1 or 3. Yep, so it is again D. Okay, so the next step is going to be a little bit more time consuming, but what we need to do is find the eigenvectors. So what are the eigenvectors to this equation? So again, we started out with 0, 1, 3, 2. Lambda 1 is equal to minus 1. Lambda 2 is equal to 3. And then what you have to do is, looks like we have a lot of people who are guessing C. Hopefully you guys all already solved this. Let's double check to see if this works out. So we have lambda 1 is equal to minus 1. So that's 0, 1, 3, 2 times xy is equal to minus x minus y. So you're left with y is equal to minus x. And so v1 is equal to 1 minus 1. So notice that it is definitely, so notice that C turns out to not quite be correct here. So we need to figure out what it actually is. So we also need to compute the eigenvalues and eigenvectors for the second one. So lambda 2 is equal to 3. So 0, 1, 3, 2 times xy is equal to 3x, 3y. When you solve this, you get y is equal to 3x. So v2 is going to be equal to 1, 3. So you have to be really, really careful when you're working through this, because if you're not careful, you end up with a negative sign in the wrong place. But anyway, the answer here is indeed 1 minus 1, 1, 3. And you guys should definitely be practicing this because this is going to be super important later on. Okay, so now the next question is, let me reset the chat. Let's reset the chat. And what is the general solution? Yep. Okay, so once you have the eigendecomposition, it is relatively easy. Oh, I have an extra comma there, which really shouldn't be there. I apologize for that. Ignore those commas. But yeah, so the answer here is indeed B, because you have the eigenvectors and eigenvalues, and this is just the general solution. Okay, well, let's continue. The next step we need to do is we need to solve the initial value problem for this as well. So our initial value problem was x of 0 is equal to 0 and y of 0 is equal to 4. And remember, from the previous slide, we had xy is equal to c1 e to the minus t, 1 minus 1, plus c2 e to the 3t, 1, 3. So we want to solve this for x of 0 and y of 0 is equal to 0 and 4 respectively. I'm going to ask you what the questions are, what the constants are. So let me just give you a hint to get started. Basically, you're solving for 0, 4 is equal to c1 e to the 0, 1 minus 1, plus c2 e to the 0, 1, 3. Or alternately, 0, 4 is equal to c1 times 1 minus 1 plus c2 times 1, 3. Okay, well, let's take a lot of you are guessing B. So let's continue working this out. So this is c1 plus c2 minus c1 plus 3c2. And so therefore we know that c1 plus c2 is equal to 0, and minus c1 plus 3c2 is equal to 4. If we add these two together, well, what do we get? We get 4c2 is equal to 4, so c2 is equal to 1. And what else do we get? And then c1 is going to be equal to minus 1. And so the answer here is actually C, which it looks like a couple of you all got here. Yeah. So make sure you're very comfortable with solving these systems of equations, because these will come up over and over again and in all kinds of problems. And the end result here is that xy is equal to minus e to the minus t 1 minus 1 plus e to the 3t 1, 3. Why does t equal 0? Ah, yes, because this is t. This is our initial value. So we decided to choose at time 0. You could have time 1 or time 2 as well as your initial values, but here, because x and y are functions of t, and we're solving for x of 0 is equal to 0 and y of 0 is equal to 4. Okay, and it looks like we've gone a little bit over for this half of class, actually. So I am going to go ahead and give you guys a 9-minute break. So be back at 1:20, and I will see you in a moment.